Buenos días a todos, bienvenidos a este webinar. Welcome everybody for this webinar. The webinar is hosted mainly by the program Energetica 2030. This is a big program and I want to talk about this a little bit. So we are just waiting a few more minutes. There are entering more people that is already registered. We have so far 42 people in the room, and we will start in 1 more minute. And the agenda for today, we're going to talk like 5 minutes about what is Energetica. Since most of the people here is speak Spanish, we're going to talk about Energetica in Spanish, just for that. And I know that Professor Monty and Andrea understands very well Spanish. Marcus, I hope that you can understand a little bit more Spanish, but you know that about Energetica. Then we have the webinar about the dynamic Phasor theory and application in power systems. And we will have a space for question and discussion. And after that, we will show what are the next webinar that we have planned for this year, and that we have that you can met here. Hola a todos, esta parte la vamos a hacer en español. Bienvenidos, gracias por la participación en este webinar que hemos preparado desde Energética y con muchas instituciones involucradas acá, incluyendo SIGRE Colombia, con el cual tenemos una relación muy importante. Y quiero contarles primero, bueno, sobre Energética 2030. Mi nombre es Ernesto Pérez, soy profesor de la Universidad Nacional de Colombia. Estoy en este proyecto Energética 2030, que es un programa enfocado a tener una estrategia de transformación del sector energético colombiano en el horizonte 2030. Y dentro del proyecto soy el subdirector de fortalecimiento institucional y el líder del proyecto P9, que les voy a mencionar más adelante. Este programa nace como un ecosistema científico por una convocatoria de Colciencias en su momento, ahora el Ministerio de Ciencia y Tecnología. Y es uno de los programas más ambiciosos en investigación que ha desarrollado Colombia en sus últimos años. Fuimos catalogados como el mejor ecosistema en su momento de la propuesta y nos enfocamos en el tema de energía, es el tema que vamos a trabajar. Lo conformamos 8 instituciones colombianas, 4 universidades acreditadas y 4 en proceso de acreditación, 3 empresas del sector, principalmente el sector eléctrico, todos hacen parte del grupo ISA. Internexa, que va a ser un factor muy importante en la parte de comunicaciones y de trabajo en la nube. Y tenemos aliados internacionales que trabajan en los diferentes proyectos, principalmente hoy tenemos una participación de RWTH, de Aachen University, y también participantes de Jülich, un instituto alemán bastante importante en Alemania. El objetivo principal de este programa es desarrollar una estrategia integral para la transformación del sector eléctrico colombiano, orientada en la confiabilidad, sostenibilidad social, económica, ambiental, en el horizonte 2030. Algo, digamos, bastante corto, pero que lo vemos que cada vez es más cerca de este. Nosotros conformamos este programa, es un programa grande, aproximadamente 290 investigadores de 31 profesiones diferentes. Participan investigadores de empresas, algo poco común en Colombia, y 48 de los investigadores tienen doctorado. Algo que proponemos es tener por lo menos 20 doctores formados adicionales más de 60 magíster y más de 80 estudiantes de pregrado participando en este programa. Tenemos 7 retos, como les decía, es en energía, entonces es bastante integral. Se hizo para mejorar la eficiencia del uso de combustibles fósiles, cómo sustituir el uso de combustibles fósiles, otro de los retos, cómo aumentar la eficiencia y la viabilidad financiera de fuentes no convencionales de energía renovable, cómo se debe operar y coordinar un sistema con profunda penetración de fuentes no convencionales de energía, cómo se debe elegir la matriz de generación en zonas no interconectadas, cuáles deben ser las características de un mercado de energía con nuevos tipos de generación y cómo resolver las barreras sociales, hábitos regionales o culturales. Algo que, digamos, es bastante crítico, al menos en nuestro país, Colombia. Tenemos 10 proyectos eh, que se pueden resumir en diferentes áreas. Uno relacionado con el consumo, o sea, un área grande que es el consumo, en donde tenemos 3 proyectos. El primero es respuesta activa a la demanda, cómo se van a comportar los usuarios en este nuevo esquema de ya no ser solo consumo, sino consumidores. ¿Cómo vamos a tener una construcción energéticamente sostenible, no solo pensando desde la parte eléctrica, sino finalmente desde la construcción? Algo que se adolece especialmente en estas zonas de Latinoamérica hacia la construcción. Eh, Finalmente, otra etapa de consumo tiene que ver con la movilidad eléctrica y se mira no solo desde los vehículos de 4 ruedas, sino también pensando en embarcaciones, especialmente tenemos zonas en Colombia en donde el transporte es acuático principalmente y particularmente Colombia tiene una gran penetración de motos de 2 tiempos y de 4 tiempos que son bastante contaminantes y se espera tener conversiones de conversión lo suficientemente económicos para poder tener una transición mucho más rápida a la electricidad. En cuanto a la parte de generación, tenemos 2 proyectos importantes, uno relacionado hacia biomasa, buscando no solo generación de energía eléctrica, sino poligeneración, muchas otras aplicaciones que se pueden dar para hacer financieramente sostenible la poligeneración y otro relacionado con la generación eólica, solar y eólica. Otros 2 proyectos enfocados hacia la política de regulación de mercados que se van a tener con estas nuevas características. Análisis de escenarios futuros, cómo serán los escenarios del 2030, cuáles son los aspectos que pasarán y de eso pues hablaremos en una futura charla de estos webinars. Tenemos otros 2 proyectos, proyecto 8 que es de pruebas de microredes con conceptos de microredes en diferentes instituciones para probar diferentes esquemas que se pueden tener en estas microredes y un proyecto que es el que yo lidero que tiene que ver con la supervisión, control y protecciones de sistemas eléctricos a gran escala, va muy de la mano con la operación del sistema con XM. Y finalmente, el proyecto 10 está relacionado a la apropiación social y alternativas de producción de consumo de energía en Colombia. Es ver cómo estas tecnologías se pueden realmente transferir, porque es uno de los retos más importantes de la transferencia. Y aquí pues participan antropólogos y sociólogos que nos están ayudando a desarrollar este punto. Como les decía, el proyecto P9 es uno de los proyectos, digamos, más ambiciosos que tenemos, enfocados en varios objetivos, pero que finalmente hacen toda la integración de los centros de control del futuro y que permitirán avisorar cómo desarrollarnos. Y aquí tenemos una interacción muy fuerte con el equipo de la Universidad de Agen y Jülich, especialmente en todo lo que es simulación en tiempo real. El profesor Antonello Monti y el doctor Martínez nos van a mostrar una de las teorías que han desarrollado en los últimos años sobre dinámica, la teoría de fasores dinámicos y la aplicación en sistemas de potencia. El profesor Monti es el líder del Instituto de Automatización de Sistemas de Potencia Complejos en el centro de E.ON, de energía, en Alemania. Y Marcus es el líder de software, de productos de software y desarrollo de modelado para simulación en tiempo real. Son los coautores de los fasores dinámicos como el DPSIM, como un simulador de tiempo real. Entonces, a continuación, vamos a darle paso a esta presentación. Muchas gracias por su presencia. Eh, Creo que se está. ¿Me pueden confirmar, Juan Pablo, si estamos grabando?
Sí, se está grabando.
Bueno, entonces quiero recordar que estamos grabando. Vamos a tener la presentación, luego de ella vamos a tener preguntas. Por favor, para la sección de preguntas vamos a levantar la mano o por el chat y vamos a estar como pendientes del tema. Entonces, muchas gracias. Y, okay, welcome, Marcos, Antonello. Thank you very much for this webinar. We are very happy to have you here. And so I give you the word. Thank you.
Thank you. Good morning, I should say, on your side. It's afternoon for us. I think it's still morning on your side. It's a pleasure to be here. It's a pity that we cannot do this in person. Originally, the idea was to have a joint conference together physically in South America. Unfortunately, given the current times, we have to move to a virtual event, and that's the reason of this sequence of seminars like the one today. But it's anyway a pleasure to be here to discuss and present the work we have been doing the last few years in the aerodynamic phasor simulation, basically in the task to find new modeling solutions that will better fit in the context of the modern power system. So I will start the presentation with a few introductory slides, then I will leave the floor to Marcus, who is the guy behind the software, really writing the code, and he will be perfectly introducing you to the features and characteristics of our software. So next slide, please, Marcus. So what's the reason? I like this picture. I'm using in several presentations now. I don't know how many of you can recognize what this is, but this is a picture of the first significant power plant ever built. This is the Niagara Falls power plant in the border between US and Canada. There was the original first development of a power plant that was feeding from the waterfalls in Niagara to Buffalo, New York, creating the first basically industrial park that was fed by electrical energy. And this power plant set the standard that stayed on for about 100 years and defined some of the key concepts behind power systems. And one of the key elements that you can definitely see here is the presence of rotating machines, and then the fact that power systems means an electromechanical systems, first of all, in which the interaction between the rotating masses and the electrical engineering side of the network defines what we call power system dynamics. If we move forward 100 years about, next, then we get some more recent development. This is a DC-DC converter built in our research center, mostly by my colleague, Professor De Donker. That's full power electronics. So after more than 100 years in which some fundamental concepts were basically written in stone and clear, we are now moving from an electromechanical network to a network that progressively is more and more an electronic network. And because here we're talking about in the context 2030, at least looking at the current ambition, I would say, of the European Union and of the member states, 2030 will mostly be already an electronic network. But what is interesting is that even if you look at today, and you look at some numbers, particularly it's more familiar with Germany, obviously, we already had instances in which the network was running with an extremely high penetration of renewables. So we have to distinguish between energy as a quantity over 1 year, a month, or even just a day. But from a power system dynamics, even 10 minutes running with a network with 100% penetration of renewables means that the presence of electromechanical devices has been dramatically reduced. It's still not zero because those rotating masses are still there, even in that situation, at least at the moment, but we are clearly going into a situation in which the presence of those rotating masses is, let's say, reduced. What that means. So next slide, please. That means that some quantities like frequency, for example, becomes a little bit harder to define. This animation is something we did together with our partner, particularly University College of Dublin. My colleague Federico Milano developed this scenario in the EU project Reserve. And what you see here is an animation on the famous 9-bus system from IEEE, slightly modified for the purpose, introducing more renewables, that while we are used to think about frequency as a global quantity, in a simple scenario like this one, already frequency, that is the color map you see on the bottom, is actually a quantity that doesn't have, first of all, a steady state value, and it's highly depending on the position, so that classical ideas of a common frequency all over the power systems are hard to support and are to keep as reference for any kind of modeling or analysis of the power system. Next slide, please. So that we can say it's a question of eigenvalue. So traditionally, when you take a power system dynamic class, the first lecture, at least that's what I was used to teach, says, okay, we have a family of eigenvalues defining the characteristics. The lowest are the thermal, then come the electromechanical, and then we have next the electromagnetic. And but obviously this is an abstraction, but we have some clear categories going from the milliseconds to the minutes. And in a nutshell, we could identify those three categories. And when we have these three categories, and we talk about power system dynamics, means particularly that electromagnetics are for us too fast, the thermal is normally too slow, and it basically is the electromechanical part. So the interaction exactly about these rotating masses and the power systems in which the electromagnetic is anyway always in steady state from that perspective, so that the eigenvalues are strictly connected to the electromechanical part of the system. But that's the classical power system. If we move forward to the modern power system, so to speak, so in this direction of more power electronics, and we look again at these eigenvalue solutions, we find that this is changing. The thermal disappears basically because based on renewables, and we cannot distinguish anymore the two big family. We got to something we can call here, generally speaking, power electronics, probably a broader range of eigenvalues anyway, depending on the control loops that and the way those will be designed. Is still an open point, how that will look like actually, but clearly the classical scenario is gone. And then clearly this means that also from a simulation perspective, we have to change. Keeping the classical structure, again, the three categories of the classical power systems analysis and look at the eigenvalue, we had the chance in the past to distinguish between the Phasor type of simulations and the EMT, electromagnetic transient simulation. Two clear categories, two types of analysis that were clearly separated. And that could require different software, different solvers that will support a different function within the power system. Again, fast forward into the future, and from the classical power system, we move to the modern power systems, and we need a tool that fulfill the new categories of eigenvalues and the new mix and not clear separations. And that's what we've been trying to target with what we call dynamic phasors. I'd like to clarify from the beginning, and I think Marcus will be even more precise than me later. We use the term dynamic phasor, even if internally I've been discussing a lot if this is appropriate, because dynamic phasor is a quantity defined in a clear standard from the PMU point of view. Our definition of dynamic phasor is broader in frequency, is more, let me say, flexible. And so it's the best name we can have at the moment. There isn't a right terminology, I would say. But the idea is that it is a phasor with time dependency. How large is the spectrum with which we analyze this phasor? It's a choice that, nice, to know from the beginning in our simulation approach, it can be done even at runtime. And that's, I think, one of the major feature and value of the work that Marcus will detail in the next few slides, because we really have a flexible tool that even online can adapt its capability of modeling. Next slide, please. A little bit more then on the motivation. We have been investigating then why we need this solution. We have been trying to find a new solution capable of real-time simulation to improve system model, and also to look at the possibility of application like digital twin. So creating a flexible model able to run in real time, able to run and learn from data. This is another important feature. And so having possibility of both scenarios offline and real time, but clearly as a major part and major interest in the real time simulation part. We want to have large scale capability. My personal dream is one day to have a very good interconnected model of the whole Europe, but at the same time with the capability to go also in the high level of detail. Those two requirements in the past were, by definition, let me say, somehow a contradiction. And so we need a new simulation approach able to change the focus and able to bring together those two requirements that originally and traditionally were in contradiction. Next. And that's basically how again, looking from standard solutions and also in the market level solution of tools that we have, again, starting from the classical definition I said before, the different type of eigenvalues and dynamics. The thermal electromechanical could be tackled by large high-performance computing clusters, so with a high level of scalability, but using basically static simulation from the electromechanical, let's say quasi-static. And then in the idea to go to electromagnetics, that means normally right now to go into custom solutions. So there are a lot of very good commercial tools that apply high-performance computing paradigm, but using custom hardware and custom bus, all the way to, if you want to get to the details of the power electronics, to include also FPGA as an option when we want to go down to the under the microsecond timescale as power electronics center may require. But we don't have a way to smoothly integrate. That's what we need in the power electronics scenario. And that's why we felt there is a need of a new approach that could do that and also allow us to have a good data management perspective. And as we'll see that later, that's also one of the tasks, is to develop something able to play with data according to standard, and so that also the integration of the operation within a utility can be done without having a different format for simulation with respect to operation. That's where this dynamic phasor modeling came into play as a solution, and basically is an extension of ideas that have been around now for a while. Here we have in the slide reference to a paper from Seth Sanders, and that was developed at MIT in the beginning of the 90s. But what we have done is to start from those fundamental theory and to develop an open, flexible, extensible solver able to support this type of challenges that have been discussing so far. Next. The other point, let's say from my perspective, last but not least, before I give the floor to Marcus, if we can also extend the time step, because we have basically capability of keeping accuracy also for longer time steps in several situations. We also support the possibility to link in real time different laboratory or different research center or even different operating center. And that's what this previous dream I told you, to connect a network of laboratory in Europe for the definition of a digital twin of Europe. But as you know, in the Energetica, this dream is going on already in Colombia. It's in a much more realistic scenario, I would say. I mean, you guys are really doing it already right now. And that's, I think it's an interesting opportunity, because particularly when you look at the research perspective, what we see, and I mean, this presentation discussion today is a proof of that. It's also a way to create collaboration and scientific exchange. And because we don't require specific hardware, we talk about democratization of real-time simulation. So everybody can use our software on every kind of PC type of platform running Linux operating systems, and then coming really to create international cooperation as the one that is behind the talk we have today. With that, I hope I gave you a good introduction on the background, the means and the goals of what we have been doing. And now I will ask Marcus to jump in and get more technical on what DPSIM is about. Of course, at the end, we'll be very happy to answer any questions when Marcus is also done.
Thank you. I hope you are really excited to get started with the next phase now. The big question is, what are dynamic phasors? Now that we talked so much about them already. Okay. I think a good way to start talking about dynamic phasors is to think of bandpass signals in power systems. So here you can see an example of a 50 Hertz signal. I call this one the carrier signal, and an amplitude modulated version of this signal, which is amplitude modulated by this red signal that you can see here. And in the frequency spectrum, this looks like this one here. So you have basically only peaks around the 50 Hertz. And the question is really, why are you considering all this frequency spectrum here up to 50 Hertz and a little bit if the information that you really want to look at is only this one here? So this is where the dynamic phasors come in. The dynamic phasors describe this envelope here. And basically they are a version of our amplitude modulated signal, which is shifted by 50 Hertz or 60 Hertz, depending on the power system you are talking about, to 0 Hertz. So that in the end, the only thing that you are looking at is the small variation around your 50 Hertz signal. So basically these smaller peaks here. That's what you are really interested in. A nice feature of this approach is that since we are not looking at the 50 Hertz plus signal anymore, but on the shifted signal, which is around 0 Hertz, we can simulate this with a lower sampling rate in our simulation. And as Professor Monti mentioned, this approach bridges the gap between EMT and quasi-static simulation. And here you can see again, the idea is quite old, but I guess the reason why it was not so popular for many years is that only now we are really looking into very high frequencies with power electronics coming into power systems. If we look at other domains, like for example, microwave engineering, approaches like dynamic phasors, maybe they call it different, like baseband representation, but they are much more popular than they are in power systems right now. Okay, so the next question is, how can we use this approach in a simulation? And for this, I want to demonstrate again why we can for the simulation time step, we can use a lower sampling rate in the process of simulating the dynamic phasors compared to our EMT signals. So if you look at this blue original EMT signal, the sampling rate that you need, or it's getting bigger, and the time step, what you can see here, is getting smaller when this red rectangle increases. And you can see that the higher my simulated signal is, the higher I have to choose the sampling rate, or the smaller has to be my simulation time step. On the other hand, if I use the dynamic phasor approach in simulation, and I eventually shift my signal to 0 Hertz, as I explained before, the sampling rate that you require is much smaller. And in the previous example, this was only shown for a 50 Hertz signal and some modulation of this signal, but you can actually use the same approach also if you have several of these frequency regions or frequency bins. So for example, here you can shift both of your frequency regions to 0 Hertz and use a smaller time step, a larger time step, sorry, a smaller sampling rate. It's always dangerous if you mix the two than before for your EMT signal. You just have to keep track, of course, of how much you shifted which region. So you have to keep them apart. And this is actually where you get not just one dynamic phasor, but 2 dynamic phasors for one EMT signal, because you have these 2 regions that you shifted. And at the end of the simulation, you just shift your signal back, and what you get looks exactly like the EMT results. You can also see this later. I will show you synchronous machine fault, and the results look exactly the same if you look at the DP, at the shifted, so post-process DP results compared to EMT. Some more theory, because the question that is asked many times is, so you can increase the times, you can increase the simulation time step, but by how much? What is the error that you do if you use a certain sampling frequency or shifting frequency? And this depends a lot also on the model that you use. But in general, you can see here a plot that shows the error independence of the used time step and the shifting frequency of the phasor for a very simple integration integrator, like an inductor or capacitor, for example, depending on which way you look at them. And what you can see here is that if so assuming that I have a 50 Hertz signal and I shift in my simulation, I shift this signal by 50 Hertz, then you end up somewhere here in this part. And you can see that the error is 0 independent of the simulation time step that I chose, which makes sense because if I have a 50 Hertz signal represented by 50 Hertz phasor, there is no change in the phasor and I can basically choose any time step. But the more the shifting frequency differs from the actual source frequency, and at the same time, when I increase the simulation time step, the more I get an error in my simulation. And this case here is basically the EMT case. So this also means that you don't have to get the shifting frequency exactly right when you use dynamic phasors. It is okay if you have a shift and, for example, a 60 Hertz signal. Here you can see the comparison of a reference signal, which is simulated at 100 microseconds time step in gray, and the DP version and EMT version with a 10 milliseconds time step. And the orange one, which is the EMT signal, is basically not usable anymore. But the dynamic phasor solution here, which is already post-processed, so that's why it looks like the EMT signal, looks quite good, even for such a large simulation time step. And now you might wonder, how can this be? I have a 60 Hertz source and a 50 Hertz shift. Where are the remaining 10 Hertz? And you can find them in the phase, which is continuously rotating with this 10 Hertz frequency. So in this case, you have one complex phasor with an amplitude. You have a phase that is changing. And another question that you might ask yourself is, what is the difference to static phasors? There I also have an amplitude, I have a phase. The phase may change over time. The difference is the causality. If you the change of the phasor in the dynamic phasor case depends on the previous time step, and not just for the electromechanical part that is connected to the network, but also for the network. For the network itself that consists of resistors, inductances, and you will see that the inductance model is really there you can really see the difference between the static and the dynamic phasor case later. But before we come to a simple model already, I would like to introduce briefly basically the main ingredient to build our models, which is how do we model dynamic systems using dynamic phasors. And what we are considering here is the differential equation part of our system. And we would like to express this in dynamic phasors. So first of all, we use the analytic signal instead of the real signal, which is constructed by having the real signal plus the Hilbert transform of the real signal. And if you take the real part of this, you get your real signal again, so nothing really changes. But it is also important to, one thing that I want to point out here is that this is one way to construct a phasor, and later you will also see other ways. So this is the first step, we construct our analytic signal. The second step is to apply the actual shift. So here you can see that we shifted our signal by our omega c, which is the carrier signal or system frequency. And this is shown by this, by these, yeah, I don't know how to call these brackets, somehow these arrows. This is usually used in literature. So this is our analytic signal, but shifted by this carrier frequency. And the question is now, if we have this dynamic phasor and a differential equation like this, how do we bring these two together? And basically, this is just using the chain rule on this phasor here. And if you do this all the way through, you can see that you get something like this, which already looks a little bit like a combination of our static phasor version and our EMT signal. So I guess this was a little bit fast, this derivation, but I want to show this at the end of a very simple model here, which is the inductor. And already use this inductor model together with nodal analysis as the solver approach. The reason for choosing nodal analysis here is that this is a very common approach used in real-time simulation, because it allows us very easily to construct from a description of the circuit to get a consistent equation system that describes this circuit topology and all the dependencies between the components due to the connections. And another nice property of this approach is that we get a deterministic time step. And this is really important for the real-time simulation. So this is not the only way how to approach this, but it's a very common way also for EMT simulation if you want to have real-time performance. So consider so we consider the inductance model here, and you can see that this looks very similar to this derivative equation that was derived. with the static phasor part and the EMT phasor part. And now, if we want to use this model in an M&A solver, this is very similar to the way how you would do it in EMT. You have some components that you can pre-compute, and which are in blue here. And you have your unknown vector, which is X. So basically, you have your stems in your system matrix A, which the stems are GL, which is the conductance here, and you have a current source in the case of the inductance, which goes into the source vector here. So I hope this looks familiar to anyone that has applied nodal analysis already. The only difference is that here we are talking about a complex matrix and complex vectors. So these parts are known, the blue ones, and what we want to get is our X vector, which are in the basic case our voltages, the node voltages. And from these voltages, we can again update the state of our component here in what is called the component post step. So this concludes the very basics. So how can you construct dynamic phasors from real signals? How can you use the dynamic models in an M&A solver that include dynamic phasors? And the next thing that I would like to talk about is, if you have this kind of mechanism for your solver, the next problem that you face, especially for real-time simulation, is even using this M&A approach, at some point, you won't be able to solve this in real time anymore for different reasons that I will explain in the next slides. So the first thing, before we run into the problems really, is the first thing that we can note is that using nodal analysis has one nice feature, which is that the component pre and post steps, so calculating our system matrix, calculating the source vectors, these are things that can be done before the system solution, and they can be done independently for all these different components. And the same for the post steps. So there is already something that we can parallelize. And this is independent of using dynamic phasors or EMT here. But the problem is that this system solution here, we cannot really parallelize like this, because we have this large linear equation system with the matrix A becoming bigger and bigger as the network grows, and we have to find ways to cope with this problem. So the question is, how do we distribute this large network? Also in EMT, there are some methods to do that. In EMT real-time simulation, diacoptics and transmission lines. And as for the EMT dynamic models of inductances, capacitors, and all kinds of things, we have also adapted these methods to the dynamic phasor case. So using either of the two methods, you can now decouple the solutions of portions of the system and compute them in different threads of your simulation. The two methods are a little bit different in that for diacoptics, you usually don't need to change your model. You don't need to, like for transmission lines, consider that the lines are long enough, introduce this special transmission line model, and so on. You can keep, for example, pi lines and just distribute the system at these pi lines. But in addition to the subsystem solution in diacoptics, you also have one meta solution basically, which brings all these solutions together. So the decoupling is not as nice as for the transmission lines, as we can also see later when I come to the results. So this is all nice if we have our basically the single dynamic phasor case, as I would call it. So if you don't have several frequency bins that you shift. But the problem comes if you have several of these frequency bins and you want to shift them as I showed before. Then you have, in this case, you have your fundamental and 2 additional dynamic phasors. And even if you distribute your network into smaller subsections, each of these subsections will have a multiple of your of the number of EMT signals that you had before, depending on the number of dynamics that you have. So each of these systems, in this case, is 3 times bigger as soon as you introduce more dynamic phasors. And this is a problem that you don't have if you do EMT simulation, because you only have, for one signal, one variable. So here we had to take an additional step. And the basic assumption for this step is that if we look at the network, so not the components. So for a component, I would say here in this case is, for example, power electronics inverter or synchronous machine. They are connected to the network. But if we are talking about the network, which is transformers, lines, switches, these usually don't include nonlinear models. And because of that, there's no cross-coupling between the different frequencies, which means there's also no cross-coupling between the different frequency bins. So we can basically assign each frequency bin to one instance of the system that only covers a particular phasor. So for this case where we have 3 dynamic phasors, we have for each subsection 3 additional systems, and each solves one of these dynamic phasors. So now, as I said, this is fine if we have linear models, but what happens for where do the nonlinear components go? Because we cannot linearize everything. Of course, you can linearize everything, but maybe you don't want to do it in any case. So our idea is that for the nonlinear parts, you can push them into these components. So if you have, for example, the power electronics model, it's nonlinear. It depends on all the different dynamic phasors. So what you can do is you compute basically your initial output of the inverter. You inject this into the different layers, frequency layers of the system, and you get, in this case, 3 solutions back for each of these systems. And then these 3 solutions are fed back into the power electronics inverter. And because we solve these steps in parallel, these steps in parallel, and these steps in parallel, we don't have a problem with the causality here. So we can always treat the nonlinearities in the pre-component and post-component steps. And this approach actually works, as I can show you later also in the results. But before we come to the results section, I want to briefly give you an overview of the software solution that Professor Monti already talked about. So we've covered now the basic dynamic phasor concept, how to model with dynamic phasors, the challenges that you face if you use dynamic phasors in a simulator, and how you can, a concept on how to solve them when you want to have real-time performance. And all of these things come together in the software solution that you can see here in the middle, which is called DPSim. And this is, by the way, open source. So you can use it without asking permission. You can extend it and use it for your research, for your publications. So feel free to look into it. And the main purpose of DPSim is actually to have a dynamic phasor-based solver library, but we also have some EMT models in there. Actually, we built quite a lot of EMT models to have an offline reference with a very small time step to compare to our dynamic phasor models. And recently, we also started to introduce a power flow solver, which is quite important if you want to run your dynamic simulation, but you don't have all the power flow results for initialization from a different software package, or you cannot import these results for some reason from the other software package, then it's quite nice to have a power flow solver as well. And so these are the domains covered by DPSim, but the main one is really the dynamic phasor one. You can run real-time simulation as well as offline simulation. And the main input format to describe your network is the IEC sim model, which is as we see it at the moment, really becoming the only solution that really works to exchange network data between different software packages. So it's really convenient to have this as input format. And of course, you can script your networks using Python or C++. Another feature is that you have connectivity, even for real-time simulations, to many different protocols through another open source tool, the Vilas framework. Yeah, and as I said, the core is actually, I didn't mention this so far, but the core is actually implemented in C++ because for the real-time performance, but we also have a Python interface, which is especially nice to do some comparison, for example, for offline simulation, comparison to Simulink and things like this, just to verify your models. So this is the software solution. And now I would like to show you some results with dynamic phasors, especially in comparison to EMT simulations. So here you can see a very easy network model, which is just composed of a synchronous machine, a load resistance, and a step. And the differences in the error if you compare the EMT and dynamic phasors. And what you can see here is, this is the time step, that we actually get quite okay results for the dynamic phasor case up to a time step of 650 microseconds, which is quite good because the synchronous machine is actually the most complicated model in this regard. So maximizing the time step is for this, the synchronous machine is really the most complicated one. And here we get good results and stable simulation up to 650 microseconds. And for the EMT case, the error is in general much larger, and it also gets unstable much faster than in the dynamic phasor case. And actually, if you compare the EMT and the DP results after the post-processing, they look fairly similar if you compare, for example, against the Simulink simulation with a very small time step here, which is in gray in the background. It looks really similar to the same, I would say, to the DP phasor simulation. Only here at the end, you have a difference because DPSim is acting immediately here, switching again, and Simulink is waiting for the zero crossing. And This is why I think this example is also nice, because here again, you have a change in the system frequency. As you can see here, the rotor frequency of the synchronous machine. And you can see that this is also reflected in the phase of the dynamic phasor. And as I said, also for a static phasor, you might see a continuous change of the phase if you do a quasi-static simulation with your dynamic electromechanical models. But the difference is that these dynamics are not correctly reflected in the network part, because you are treating the network when you use the classic static phasors as static model. Okay, so this was a little bit demonstration on the accuracy between dynamic phasors and EMT. And next, I would like to show how these concepts that I talked about before regarding the parallelization, how they actually perform if you run a real-time simulation on a decent sized grid. So here we look again at the famous 9-bus system, but in this case we have multiplied this 9-bus system and interconnected the copies of the 9-bus system. This was a very easy way to get a variable sized network, and we used up to 20 copies, interconnected copies. And here you can see the simulation time step here. And the blue one here, the coupled one, is the case where we only parallelize the pre and post component steps of the MNA. The green one is the diacoptics approach adapted for dynamic phasors, and the orange one is the adapted transmission line parallelization. And you can see, first of all, you can see that for these cases, we are well below the 1 millisecond time step for real-time simulation. And the second thing is that the transmission line simulation, the simulation that used the transmission line decoupling, is much faster than the one using diacoptics. But for the transmission line model, you have to consider that you use that you cannot use any time step basically, and any combination of line lengths. I see comments in the chat. I don't know if there were comments before, so I'm sorry if I didn't. No, this was the first one. Okay. It's a little bit long to read, so I will take this one later, I guess. Okay, so yeah, so this is on the parallelization of the subsystems. I think both methods are really interesting. Diacoptics and transmission line, it really depends on what you are looking for. For the diacoptics case, very quickly, you can also see splitting the network more and more doesn't make sense. So here you can see the optimal split number. And for multiple threads, it saturates at some point, because splitting more and more also means more overhead for this meta solution, as I said before. Introducing more splits for the transmission line system doesn't have so much overhead. Another interesting result on the parallelization, but this one is really artificial, I have to say, because before we looked at this 9-bus system, which is a normal grid, I would say. Here, we really wanted to see what happens if we only consider this parallelization that we can do of the pre and post component step, and then reduce the network, shrink it down to a really small, really small network, just to see what is the advantage of parallelizing the components. And in this case, it's the opposite compared to before. Here we had the big bubble is the task with a big simulation time, and this is a computation time, and this is here the network solution. And here it's the opposite. So here we simulated a very simple network, having synchronous machines, and this is basically the network, so only run resistance, and then up to 20 synchronous machines connected to this network. And you can see for the 2 synchronous machines, this is the network, this is the synchronous machine model. So here the component is really the dominant, uses the most computation time. And you can see that if you look at the computation time, the overall computation time here, even without using diacoptics, transmission lines, just parallelizing the pre and post component steps, using more and more threads, we can bring down the simulation time. So this is not really, I would say, a realistic network, but it's nice to see that it actually behaves as we thought it would behave. The last thing that I would like to show, because so far we only talked about more or less the classic network with the synchronous machine, the error, and the simulation time that it takes. But as Professor Monti said, we are introducing more and more power electronics. And this is where dynamic phasors become really interesting, because for the synchronous machine case, you can get away with one dynamic phasor. You have your 50 Hertz shifted phasor, some variation around the 50 Hertz. You don't need really more phasors. And if you have power electronics, this is changing dramatically, at least if you don't use the averaged inverter model. If you consider the harmonics, and we did it using harmonic analysis based on this book here, you get your fundamental phasor and phasors for all the combinations of the system frequency and the switching frequency. And you can inject these phasors into your network solution, as you can see here. So basically you have multiple voltage sources and they are all injecting into the network solution. You get your network solution back in this DP inverter model after one complete iteration. And based on this, you can compute, you can update your voltage sources. And here is where this nonlinearity comes in that I talked about before. This control that is controlling this inverter model here might be dependent on multiple frequencies here. And this is why you have this cross coupling, at least in the DP inverter model. And we use this DP inverter model to replace the switching converter in this simulation model here. So in the DP case, you take away all the switches and replace them with the voltage sources. And this is a comparison of this dynamic phasor model compared to Simulink. On a broad scale, it looks completely fine. If you zoom in, you can see that the ripple of the dynamic phasors doesn't, so this is again post-process. Maybe I should mention this. Here we already took multiple phasors, 8 in this case, in addition to the fundamental, and put them all together and shifted them back to get an EMT-like signal. And this is the result here. But you can actually get better. The more and more dynamic phasors you add, the more accurate become your results. And this is maybe drastic because you don't need this kind of detail in all the cases, but it's nice to know that you can get there if you just use dynamic phasors. The problem is, as I said, before I talked about 3 frequency bins that you could use in the simulation and that are each shifted to DC. But if you go to 28 frequency bins and your fundamental, you are really increasing your even if you have just very few nodes, like in this case here, you are increasing your network size dramatically. Having for each EMT variable, for each EMT voltage, you get 29 dynamic phasors. And in this case, you really have to do the parallelization that we discussed before to get real-time performance. Even for this small example here, you can see a big difference already. So this is the monolithic version where you have your system matrix, which is increased by these 28 dynamic phasors, and this is the split version. And although it's not so much in this case, because the matrices, these 29 matrices that you get out of this are very small, you can see that, first of all, this is a lot faster having the split, and it becomes even faster if you add more threads. And this will be a lot more if your network size is, if your node number is bigger. Yeah, this brings me to the conclusions. We think that the dynamic concept is really nice for this integration of EMT and DP, and especially for increasing the simulation time step for various reasons. This can be to interconnect simulators, to run on off-the-shelf hardware, can be different reasons why you would like to increase your time step. But I would assume that the current trend of going to FPGAs to get smaller and smaller time steps, if you continue in this way, it will become more and more difficult as power electronics become faster and faster, from kilohertz maybe to megahertz switching frequency. I wonder if you can keep up if you want to do this in EMT in real time using FPGAs and technology like this. So I think dynamic phasors is really a nice way to completely get around this race between simulation time step and in the end the switching frequency of your power electronics. With DPSim, we already took some steps. Actually, there are already several publications also in dynamic phasors, especially when you look at classic power systems here, you find a lot of publications about the shifted frequency approach and how to simulate a synchronous machine. But I think what was really missing so far is something that you can start from. So you don't start completely from scratch. And I hope that you find DPSim interesting, because we have already started to explore different concepts here to model classic power system components, power electronics in real time, and even speed up the simulation. And some things that are ongoing and future work. So we already started to go from the CPU to GPU. Especially, this is especially nice if you have large system matrices that for some reason you don't want to split using diacoptics or transmission lines. And first tests we already got for this 9-bus system, I think a speed up of 2 to 3, not using any smart techniques, just using the GPU, which is really cool. Future ideas that we have really not started to work at yet is to integrate nonlinear models into the network solution. This is quite bad for the parallelization of dynamic phasors, because then the assumption doesn't hold that I stated before. But on the other hand, you can expect a better stability for example, for the synchronous machine model. So yeah, there's a trade-off again, but I think it's interesting to explore this direction as well. And at the moment, we are modeling in C++, which is not super user-friendly. So we are also looking at different ways alternatives, how to, for example, use Modelica models, generate C code, and integrate this in DPSim. This is my last slide. Yeah, here you can just find a bunch of to to the simulator, documentation, GitHub repository. There are not too many action going on in the GitHub repository yet, issues and so on, because we are mainly working in GitLab, in our university GitLab, which is also public, by the way, so you can see everything that is going on there. But I think for wider public, the GitHub repository is more appealing, and also the main two applications that explain DPSim. Yeah. With this, I conclude my presentation. It was a little bit longer than expected. Sorry for that. Maybe I hope that we have time to cover the questions here. I'm starting to read them now.
Thank you, Marcus. Thank you, Professor Monti. It was really, really nice your presentation. Thank you for having here. There are some questions. I think you can see some of the questions the chat. So if you don't mind, you can read it, or really you can read it.
I think I can read them myself. So the first question is, what is the relation between stability simulation and the dynamic phasor? Basically, as Marcus explained, depending on the time step we use in a dynamic phasor representation, we go from stability analysis to EMT representation. So it's a more comprehensive approach. Of course, when we expand the time step in our simulation, it really looks like the stability analysis simulation. But when you reduce, you have the capability to focus on details. So that's why also we see this modeling approach capable of in real time adapting time step depending on the requirements and the specific questions you want to ask. So let's say the stability will be a subset, classical stability is a subset of what the dynamic phasor could cover in a nutshell. Dynamic phasor equal to synchro phasor. Yeah, that's the second question, and that's what I was briefly mentioning in the beginning. We use this name because there isn't a better name at the moment, I would say. So we started from the definitions of dynamic phasor are coming from the synchro phasor standard, but mathematically speaking, if you look at what Marcus presented, this is broader than this. I published together with some colleagues a paper on electrical power system research that been announced exactly today on LinkedIn. If you go and look at that paper, there is a lot of theoretical background on the difference between the different modeling approach and different transformation. At the end, what we could say is that under certain conditions, our dynamic phasors are the equivalent of the analytical signal coming off Hilbert transform. So it's more than a synchro phasor. But we decided to use dynamic phasor name because it's something that everybody understands. And so it's a more intuitive, not maybe being the most formal and the definition that we should use. It's another question, how do you include damping effects into dynamic phasors? Well, if the network has damping, it will come from the transient. So it's not that we have to include this in specifically. So depending on your model, the damping effect can be in the system and will show up in the time domain simulation. So it's a time domain simulation. In that respect, damping appears as a time process. It's different from working in phasor. Whenever I introduce this topic in my class, I always say, when I was a student, my professor would have killed me if I was saying that I'm doing phasor in time domain, because there were clearly two separate words. And right now, what this theory is showing that actually there is a way to interpret in the time domain in a complex signal, that is what we simulate, as a frequency shifted representation of a time domain waveform. That's basically what we are doing.
Now, in some way, you can also think of it of a DQ transform, but having not just the 50 Hertz rotating frame, but several rotating frames. And if you look into literature, yeah, as I said, shifted frequency analysis is used, SFA, to describe more or less the same concept. Complex envelope is also used sometimes, especially if you go outside of the power system domain. Baseband representation. Yeah, so they are, it depends a little bit on the derivation of the phasors. So if you look at baseband or shifted analysis, the way is more the Hilbert transform and so on. If you look at what Sanders did, it's more the Fourier way to this harmonic analysis that I showed before to get this dynamic time, how do you time dependent phasor. So the result is always very similar, and I think you find interesting sources looking for any of these keywords, basically.
Okay. Next question: is possible to reduce the system metric during the real-time simulation, for example, in the case of partial blackout? Correct me, Marcus, if I'm wrong. Right now, we don't manage in real time to change the metric structure. Is that right, or am I wrong?
At the moment, we are not completely independent in changing the system matrix, but what we already do is, if you have switches, for example, we pre-compute the different versions of the system matrices and then switch from one time step to another between these system matrices and also the factorizations of these system matrices. So basically without any delay. And something that might be interesting in this regard is that some partners that we are working together with now, they are interested in things, for example, like how do you call it in English? The intelligent transformers, step changers, and so on. And
online type changer.
Yeah.
Online type changer. Or
yeah.
FTP.
Yeah.
LTC.
So if you introduce this and you have the basically this adaptive transformer ratio, then it's also nice to be able to change the system matrix. And we have started to update the system matrix during the simulation with this model already. But it's not done yet, but we are seriously going in this direction. It's not just outlook, but we are working on it.
And then there is a more, let's say, commercial questions. Can you talk about your cooperation with OpenRT to integrate DP to their solver? There is a concrete discussion going on. What I can tell you that OpenRT joined our so-called Forschungscampus in German, so research campus. So they have now people that are part of their company working full-time in Aachen. And that's because they really value the cooperation with us, particularly because of DPSIM. We are also working together writing research proposal to analyze the application of DPSIM in some concrete real case. So there is a very concrete interest where we are cooperating and doing experiments together. At this point, I cannot tell you if and when there will be an official commercial release of DPSIM that OpenRT would like to do. For the moment, it's more a cooperation on the research level, and we haven't discussed yet, let's say, any commercial term. But if some of the projects we're doing together will continue and take off, I can imagine that this will come. Is it possible to do co-simulation with RMS simulations? The answer, I think, very easy, yes. We have done co-simulation between our DPSIM and other platform. it was probably briefly mentioned. Also, we have this set of tools called villas. Yeah, thank you, perfect. So through the villas node, you can link different solver and software together. And so the DPSIM is part of the community of the villas node, which means that for all the software that you see here or tools and whatever, there is a way to exchange data even in real time between DPSIM and whoever is the other. So for example, co-simulation between DPSIM and OPAL, classical OPAL EMT, or DPSIM and RTDS, to be fair representation to both commercial are possible. So in principle, this is not a problem. What is the size of the largest network you have used simulated in real time and the number of cores? Marcus, you're probably more prepared than me on this question.
Yeah, we have also in the first publication. I think you can see an example of 40 copies of instead of 20 of this 9-bus system. So roughly 400 nodes. That's, I would say, the largest network that we have simulated so far. And we always used 12 threads as maximum at the moment. Because we also never wanted to exceed with the threads the number of cores. So it was we had 12 real cores in the CPU to answer that question.
There's somebody that should be in. There's somebody that should be in mute. That is getting some background noise. Could you please double check on your computer if you are in mute? Apart from Energetica and Marcus, of course. Thank you.
Yeah, so 12 cores and 12 threads was the number, but there's no reason not to go higher if you have more cores. And maybe related to this, does the Dockerized version of DPSIM introduce a significant overhead to the real-time simulation on bare metal? Yeah, the results that I presented here are all bare metal. Fedora installed directly on a quite capable server. But we are more and more also project-wise, we are more and more looking into running DPSIM in the cloud now. We are doing, actually, I have to say I'm using DPSIM most of the time in Docker. But if I really make measurements, I always use the bare metal version. But I didn't do a good comparison yet, but this is something that we are also discussing quite a lot. And yeah, because we are basically, we want to offer DPSIM as a service. And if you do this, running it bare metal is not really a good option. So this is super interesting. If you get any results on this before us, I'm really interested in that. Yeah. The connect DPSIM with Kafka using MQTT, RabbitMQ. We haven't introduced data in Kafka yet, but we are using RabbitMQ and MQTT all the time together with Villas here. So basically we have DPSIM through Villas and then RabbitMQ. This is actually the setup that we are using predominantly. So it should work, I would say.
And there is a little bit more theoretical questions about aggregation stage. How are higher harmonic aggregated to the main dynamic phasors? It looks like to me very similar to a time-dependent version of discrete Fourier transform. It could be, it doesn't have to. This is the main point. So how you aggregate, it's up to, it's basically something you can set in the simulation. The easiest way would be to think in a sense, as you say, in a sort of time-dependent Fourier. This may be suboptimal in many cases. This is a very interesting research question, actually, to understand how to create those cluster of shifting. So how many how many bins basically we need and how broad these bins should be, where we include a section of the signal we are analyzing. There are work in this direction. There is a transformation called Hilbert-1 that is actually optimizing this. And the main thing is it's not a transformation that a priori you know how it works, but it requires a pre-analysis of the signal before you can define the terms of this operation. That means that one option or solution will be to have some preliminary information offline, running a simulation, for example, as EMT, to get some information about the frequency content and to optimize how you slice basically the frequency content in the optimal way to minimize the number of phasor, let's call it that way, of the components of your analysis, instead of going for the Fourier that many times the impression is that would be requiring too many bins, let's say, compared to what is the practical representation. So it's a flexible degree of freedom that for the moment we haven't seriously analyzed. The tendency is to move away anyway from simply using a classical Fourier type of slicing of the spectrum.
Yeah, and then to get back, I'm not sure how this what you mean with aggregated, but to put all these phasors together again, that is another question here. How are higher harmonics aggregated to the main dynamic phasor? So you have your different dynamic phasors. You shift them using e to the power of your omega, depending on the frequency bin. You sum them up and you take the real part, and basically that's your aggregated signal. When you take the real part, you, in the best case, get your EMT signal.
The other question will be simulate transient due to failures that can have up to tens of kilohertz component. Not sure we did failure analysis, but the inverter case that was shown by Marcos include also kilohertz level component.
Yeah,
So,
and yeah, we had this one. This I didn't show previously. I'm already in the backup slides here, but this is actually inverters and a drastic load change here, as you can see. But in this case, only using one phasor. And also, this is what I want to show actually. Here we also have a fault. And yeah, we have high frequency components in this. And this is why for this simulation to be very accurate, we have to go to a time step that is very small if we really want to simulate this failure. And we don't split this high frequency part into several dynamic phasors. And this is something that we have not done in this case. So we have done basically high frequencies for the power electronics case, where using Fourier analysis, you can get your higher frequency bins, and they are more or less I don't know, stable is the right word, but they don't completely disappear and reappear like for the failure case. And we have also done this kind of high frequency simulations here with only one phasor, but we haven't done this kind of simulation and this kind of step with several phasors, because for this case, in the moment of the failure here, you would need to know what are the frequencies. You would need to do some kind of analysis, maybe Fourier again, and then branch out, I would expect, to be able to have these several frequency bins that you shift and then simulate with a much larger time step. So this kind of unexpected failure in comparison to something that you can expect, like the switching of the inverter, is more difficult to address with this separation in different frequency bins and so on. But you can
But you,
always get EMT accuracy
yes,
by reducing your time steps. So this
exactly.
is something
That's what
that
I want to say.
yeah.
That's exactly the idea. That when you need to jump into details, the easiest thing is simply to slow down, like it was an EMT will
Yeah.
be in any way faster than the classical EMT, as Marcus showed before.
So you always have this emergency solution.
Exactly.
Okay, Professor Antonello and Dr. Marcus, thank you very much for your presentation. It's very interesting, this topic, because it takes us to a new reality of simulation. We're cooperating really close to set up this DPC, and we want to do it in a large scale. That's why Mauricio is asking about what is the largest one. We want just to get with Colombia, probably a larger one. We are setting some new equipment that we have up to our two processors of 20 cores. So probably we will have enough capacity to make a larger one and then interconnect them. Okay, that's one of the things. I hope we can see this. One of the things I would like to share with you, we are, as I mentioned, this is a webinar or a seminar that we want to do it in person. It was supposed to do it in May or June, but unfortunately we couldn't, and we take this strategy. But I think it's really nice to do it as a webinar because we want also to discuss several subjects. This is so far the preparation that we have for the whole webinars that we are having. Some of them are some presentation as we have today, but some others it will be like a roundtable that we want to discuss, more panelists that we want to discuss some challenge that we have. So this was the first one, Dynamic Phasor. Thank you, Antonella and Marcus, for this. We will have the next one at the end of August, something related with future scenarios that we are foreseeing in the electric sector. XM is our system operator that we present this. That is part also of the project of Energetica 2030. And then we have Professor Andrea Benini that is here also, is going to chair this panel for real-time simulation advantage for large infrastructure. So that's why we start with this conference today. So understand what we are doing with simulation and techniques for simulation, and the idea here is what we can do in a large simulation in real time. So what is the largest one that we can go, and why we want to do something like this. So it's very interesting, and we want some interaction between what we are doing in the project, the 2-week and some others. So if there is some others people interested here, you can just go to Energetica webpage, go to the contact, and just send an email. But you can also, I will show you my email next, and you can contact me. Also, we want to share with you the co-simulation framework that we are doing in this project. With the hand on Agen also, we are focusing on something that we can interconnect several real-time labs that we have here at Medellin, and probably we can connect it everywhere. But also we are doing some EMS of the future that can also run in the cloud. Some techniques that we want to share with you. And this is a very nice topic, the scene that Marcus mentioned. There is a driver just to make the simulation, but also to interact with other things that we have. So the common information model is a driver for a power system. It is more implemented in Europe, in the United States, but here in Latin America, we have less implementation of that. We have some experience and we want to share what we are, share that. It will be also a panel in this topic. And there are some other companies that we have previous talk that they want to share with us the experience that they have implementing in real cases the thing we are preparing this. Another topic is about some of the models for inverters for electromagnetic transit, especially for short circuit studies. We want to share with you these and some of the results of short circuit, especially in Colombia. We have a large presentation that we are having in a week network on the north of Colombia. And it's very interesting, all the things that we have found so far that may be very important to take into account when you are setting the relay protections. And the two next topics, I think it's really interesting because we are foreseeing some new things that are coming from the cloud opportunities for energy sector. What is the cloud opportunities? And also the vision of open source and open data. So as you see, DPCM is open source and it has so many advantages. What will be the future of this type of software data that will be open, where we can go with this? So this is the preliminary dates. We will invite you for register for the next conference. So really, I'm really happy for the participation of all the people who could connect here, and especially for Marcus Antonello. It was a pleasure to have you here, unfortunately virtually, but someday, I hope next year, we can have some interaction in person again.
We hope so.
Thank you for having us.
Yeah, thank you very much. It was a pleasure. Thank you for the questions, and the interaction was really interesting for us to get your questions and comments.
Okay, so thank you. See you next webinar.
Bye-bye.
Bye.
Ciao.
Ciao.
Ciao. Ciao.